For decades, textbooks called the moon a dead, dry rock. But in 2025, something isn't adding up. In 1976, the Soviet LUNAR 24 probe drilled 2 meters into the surface and returned a small core sample. About 0.1% of it was water. That finding alone should have changed everything, yet it was dismissed as contamination. Now, with modern instruments and high-resolution scans, we see water recorded where textbook logic said it couldn't persist. Ice shows up in shadowed craters, even near caves that could shelter humans. So which is it, missing water or missing tools? To find out, we need to start with the first overlooked clues. The forgotten clues from Apollo and Luna. When people think about the search for lunar water, they often picture modern orbiters or rovers. But the trail actually begins with the last breaths of the Apollo and Luna missions. Long before anyone imagined using ice for rocket fuel or habitats, faint chemical signatures were already hinting that the moon was not as dry as we believed. In 1976, the Soviet probe LUNAR 24 landed, drilled nearly 2 meters into the ground and returned a thin core of soil, just 170 grams, but enough for scientists to measure. Roughly 0.1% of that core contained water. Even more telling, the deeper the sample went, the stronger the signal appeared. It should have been a paradigm-shifting result. Instead, it was dismissed as contamination from Earth or the lander itself. Apollo samples told a similar story. Across several missions, geologists received hundreds of kilograms of lunar rock and regolith. Within them, labs began reporting faint traces of hydrogen and hydroxyl, chemical markers closely tied to water. Once again, they were set aside as accidents, stray molecules sneaking in from the air on Earth or handling errors in the lab. And at the time, that explanation wasn't unreasonable. Lab methods in the 1960s and 70s weren't refined enough to separate indigenous lunar signals from environmental moisture with absolute certainty. To most researchers, the concept of a water-bearing moon simply conflicted too strongly with established models. The dry moon consensus left little room for anything else. But decades later, that archive of material was revisited with new tools. Improved microanalytical methods, sensitive enough to detect structures within single mineral grains, were capable of probing the samples again without the same ambiguities. These techniques showed the hydrogen-bearing signatures were not clinging to the outside of the rocks or seeping in through storage. They were embedded within the crystal structures themselves, locked there since ancient lunar processes. What older instruments had treated as background noise now emerged as credible, indigenous water. The conservatism that once buried the idea had protected the samples long enough for a new generation to recover their secrets. The result was a quiet but important shift. Suddenly, the moon no longer looked like a pristine desert left behind by a primordial giant impact. Volatiles clearly could persist if protected in minerals or sealed beneath the surface. That realization mattered not only for understanding lunar history, but also for planning the future. Any measurable quantity of water transforms mission logistics. It becomes potential drinking water, breathable oxygen, and even rocket propellant when split into hydrogen and oxygen. What the early Apollo and Luna samples suggested, modern science was now confirming. And the story didn't stop in the lab. By the late 1990s and early 2000s, orbiters scanning the surface began detecting spectral hints of water molecules across unexpected locations. Later, a breakthrough came in 2009, when NASA's LCROSS mission deliberately impacted near the moon's south pole. Instruments observed the debris plume kicked into space, and within it, water vapor appeared unambiguously. Estimates suggested around 5.6% by weight at the impact site, far more than the tiny traces once relegated to possible contamination. For the first time, in situ proof existed that water wasn't just hiding inside minerals. Under the right conditions, it was literally frozen in the ground. Looking back, it becomes clear how much time was lost. If the Apollo and Luna data had been trusted at face value, the conversation about lunar water could have started a generation earlier. New mission plans might have incorporated strategies for volatile preservation decades before LCROSS. But science doesn't advance evenly. Consensus often resists surprise, and only when fresh evidence arrives from multiple directions does an overlooked clue become undeniable. The overlooked history of these first samples leaves an instructive lesson. Even today, with high-resolution spacecraft mapping deposits from orbit and robotic scouts plan to dig for ice, we recognize the pattern. Signals appear, interpretations clash, models bend. The moon's water isn't spread in neat or predictable ways. It's patchy, inconsistent, sometimes abundant, and sometimes absent where theory says it should be richest. Those contradictions stretch forward from the Apollo labs into current exploration, a reminder that understanding this resource will require more than just believing what we think we know. From faint traces in sealed vials to impact plumes erupting with vapor, each milestone pushed the consensus further from the old image of a bone-dry world. But finding water at all was only the beginning. The harder question has always been where it hides, and why it survives in some places while disappearing in others. That puzzle leads directly to the moon's most extreme environments, where sunlight never reaches the ground and temperatures drop hundreds of degrees below freezing. Here lies the next chapter in the mystery. The coldest traps in the solar system. At the lunar poles lie regions shrouded in permanent shadow. Because the moon tilts only about 1.5 degrees on its axis, sunlight there never rises high enough to touch certain crater floors. These places, sealed off from direct warmth for billions of years, create natural freezers. Temperatures inside some of these permanently shadowed regions, or PSRs, fall below about -170 degrees C, cold enough for water ice to persist over geological timescales if it is present. On paper, it seemed simple. If a crater floor never warms above that threshold, it should trap and preserve water indefinitely. For years, that was the assumption. Models predicted that every shadowed basin would be a clean vault, storing ancient ice in predictable layers. But when spacecraft began scanning those areas more carefully and ground truth from missions became available, the reality did not align. Some craters contained concentrated pockets of frozen material, while others, under nearly identical conditions, revealed nothing. The problem turned out not to be scarcity, but patchiness. Instead of finding steady sheets of ice spread across the polar terrain, instruments showed haphazard clusters of deposits. A clear example was the LCROSS mission in 2009. NASA deliberately steered a discarded rocket stage into Cabeus crater near the South Pole, sending a plume of material high enough for instruments to observe. The analysis of that plume revealed water at concentrations of roughly 5.6% by weight, a striking confirmation that at least one shadowed site harbored abundant reserves. Yet just kilometers away, equally shadowed features yielded almost no comparable signals. That kind of variability has persisted across measurements, forcing scientists to reframe what cold traps actually represent. In the late 1990s, the Lunar Prospector mission first detected significant hydrogen signatures near both poles, hinting that large ice reservoirs might exist. Subsequent orbital studies refined the picture but didn't eliminate the contradictions. For instance, Japan's Selene mission, also known as Kaguya, recorded spectral signatures suggesting frozen material at both high and mid-latitudes. Later, studies using the instrument suite known as the Moon Mineralogy Mapper and related retrieval methods even detected possible concentrations around 2 to 3 weight% on the sunlit inner wall of Shackleton crater. Such results were surprising. If sunlight regularly grazes portions of a crater wall, traditional reasoning says any volatiles there should evaporate. Yet measurements implied water-related features persisted anyway. Closer inspection from more sophisticated instruments sharpened the puzzle. Remote sensing designed to distinguish between hydrogen bound inside minerals and true ice concentrations suggested the hydrogen signal spread widely across polar regions. But when landers and rovers attempted to sample the soil directly, the story narrowed. In some testing zones chosen by NASA ahead of the Viper rover's upcoming explorations, data indicated strong ice signals buried beneath just a few centimeters of soil. In nearby zones, with almost identical conditions on the surface, the probes found dust and regolith with little trace of volatiles. That inconsistency reshaped the conversation. If the moon's poles behaved as perfect cold vaults, the distribution of ice should be uniform. Instead, the terrain functions more like a patchwork, where geology and microclimate matter. Some deposits hold in place thick layers beneath protective soil, while others are absent altogether. The explanation may involve subtle influences, the angle of a crater's rim, variations in slope, or even how light scatters off interior walls. Laser altimetry has already shown that what looks like complete darkness isn't always absolute. Reflected sunlight from crater peaks can introduce faint glows strong enough, over billions of years, to drive away exposed water. Micrometeorite impacts provide another likely factor. The lunar surface is bombarded constantly, and even tiny projectiles can churn the regolith, burying ice deeper or releasing it to space. In addition, some theories suggest hydrogen atoms migrate across the lunar surface, bouncing step by step until captured in regions cold enough to stabilize. If so, then polar ice isn't static at all, but part of a dynamic cycle of sublimation, transport, and retrapping. The Patchy distribution would then be a natural outcome of this ongoing movement, a process still unfolding even under today's conditions. For exploration, the irregularity has consequences. A permanent shadow no longer guarantees usable material beneath the soil. Mission designers can't assume drilling at any crater rim will provide immediate access to ice. Instead, they must navigate an environment where promising sites cluster unpredictably, and reconnaissance is essential. NASA's Viper rover has been tasked with mapping these variations, tracing differences between adjacent PSRs, and measuring depth as well as abundance. Each detection raises a new set of questions. Why here? Why this depth? Why this concentration? And beside each rich discovery lies the frustration of its absent twin, only a few hundred meters away. The broader picture now looks less like a uniform polar reserve and more like scattered opportunities. For human settlement, that demands caution. Extracting water from clustered pockets is logistically different than tapping from a continuous sheet. Engineers must design systems resilient to variability, with contingency planning for both rich and lean terrain. More importantly, they must know whether discovered reserves will last. A patch of ice useful today might degrade under continued extraction or natural processes. Conversely, recognizing sites where hydrogen is still migrating inward could help secure sustainable sources for future use. Even so, the irregular results carry some optimism. That concentrated water exists at measurable and recoverable levels has been proven repeatedly, from crash impacts to orbital sensors to reanalyzed samples. The abundance might not be everywhere, but it is real in some places, and in sufficient concentration to matter. The challenge is efficiently mapping those places in advance, rather than discovering them only by costly trial and error on the ground. The lunar South Pole remains the prime target for upcoming missions, but with much sharper caveats than once imagined. Some giant basins long considered promising have been reassessed and found less compelling after updated data failed to confirm volatiles. In their place, smaller sites or unexpected ridges have risen to priority status, hinting that on the moon, scale or symmetry doesn't dictate water's presence. Every mission refines the list, and the list changes constantly. The moon therefore hosts what should be perfect natural freezers, and yet the comparison between neighbors breaks expectations. Some vaults clearly preserve ancient material, others, despite the same cold and shadow, hold none. So the moon has cold vaults, but not all vaults keep their treasure. Why? A glimpse beneath the surface. While the poles are an obvious starting point, some of the most important signals about lunar water have been coming from beneath the surface. Orbiters had long noticed irregular hydration signatures outside of shadowed craters, especially across the equatorial regions. Sometimes the signals faded with the rising sun. Other times, they returned as temperatures fell at night. This made many researchers skeptical, assuming the data represented nothing more than a thin, unstable film coating the dust. But that picture began to change as new instruments probed deeper into the moon's crust, using radar to search for hidden structures and to explain where these erratic traces might come from. What the radar revealed was not just small deposits of ice clinging to grains, but entire cavities hidden underfoot. Among the most striking targets were suspected lava tubes, hollow tunnels left behind by ancient eruptions. Their existence had been proposed for decades, largely inferred from surface pits that looked like collapsed skylights. But recent radar mapping has moved them firmly from speculation into confirmed reality. In 2024, a study published in Nature Astronomy reanalyzed radar data from NASA's Lunar Reconnaissance Orbiter. The results were striking. One pit in Mare Tranquillitatis connects to a cavern-like lava tube, an entrance roughly 45 meters across leading to a passage extending 30 to 80 meters long, with walls that may continue 130 to 175 meters below the surface. For the first time, evidence demonstrated that some of these voids are not only intact but accessible. Inside such features, conditions are dramatically different from the bare lunar surface. Instead of date-night swings from blistering heat above 100 degrees C to freezing darkness below -170 C, models suggest the interiors stay close to thermal equilibrium. Some calculations indicate areas close to the cave floor could hover around 17 C, 63 degrees F, a steady and habitable temperature that would protect both equipment and people. Even where the rock runs colder, the caves insulate against extremes. Shielded from micrometeorites, cosmic radiation, and direct sunlight, these environments provide natural safe zones that the open plains cannot. This stability is also exactly the sort of condition that could help preserve volatile molecules such as water if they exist there. It is important to be cautious. Just because lava tubes are stable does not mean they are automatically icy. Radar does not have the resolution to distinguish between bare stone and frozen volatiles. Instead, what it shows is the architecture, protected voids that could, in theory, harbor ice and hydrated minerals if they were trapped during ancient volcanic or impact events. The discovery of a connected pit and tube in Mare Tranquillitatis proves that such sheltering spaces exist. It also suggests that similar caves remain undiscovered across the moon's Maria and highlands. But until rovers or drills enter those spaces, any claim of ice within them remains an informed hypothesis. Even without guaranteed water, their value for exploration is immense. The potential to use them as natural bases is hard to overlook. On the surface, constructing habitats capable of resisting radiation requires burying structures beneath meters of regolith or hauling heavy shielding from Earth. But inside a lava tube, the environment provides much of this for free. A settlement could potentially be carved inside the rock, with artificial walls sealing off sections to hold breathable air. The caves become both protective structure and promising resource repository in one. The interest in subsurface exploration has only grown with China's Chang'e 6 mission. Returning samples from the South Pole, Aitken Basin in 2024, Chang'e 6 delivered not just soil and rock, but also valuable radar observations. Surveys from orbit before landing showed reflections consistent with layered voids where fractures intersect ancient basalt flows. These radar paths traced what looked like internal chambers, some linked to skylights that opened directly at the surface. Within them, temperature models indicated conditions stable between -20 and -30 degrees C, still cold, but far better than the exterior, and cold enough that volatile deposits would not sublimate away quickly. The new samples, analyzed back on Earth, also hinted at unusual geochemical histories, possibly pointing to mantle sources with heterogeneous water content. Together, the radar maps and physical material give researchers reason to believe that water inside the moon is uneven, not only on the surface but at depth. For mission planners, the implications are practical. Persistent resource patches are required if humans are to live beyond short visits. Extracting thin films across broad areas is inefficient, but tapping into subsurface stores shielded underground could yield sustainable supplies. Even if the tubes hold only hydrated minerals, those could be processed with far lower losses than loose frost scraped from a crater rim. The accessibility of the Mare Tranquillitatis pit adds a crucial point. Exploration of such environments is technologically feasible. Cameras and instruments could be lowered with tethers, or small robotic scouts could be sent down to map corridors, testing for ice before humans commit. These are challenging tasks, but they are within the reach of near-term missions, unlike the kilometer-scale drilling that surface approaches would require. Still, the unresolved questions keep scientists cautious. Radar's reflections may look like guarantees, but until direct sampling confirms ice or hydrated rock, there is no certainty about the quantity or reliability of what lies underground. Some tubes may be completely dry. Others could hold dust or basalt rubble without volatiles. Yet even the worst-case scenario still provides enormous advantages in habitability. Empty caverns can host equipment and habitats shielded from the external environment, while the best case includes both shelter and the very water that crews need. This perspective reframes the scattered signals seen from orbit. Instead of dismissing the patchiness as sensor error or transient films, many researchers now consider that what we see on the surface may simply be leakage. The daily hydration shifts could be tiny molecules moving between shallow regolith and deeper reservoirs sealed by volcanism. The reality of the moon's water may not be on the surface at all but safely buried, waiting where the extremes of space cannot touch it. Planning for Artemis relies on this updated view. Several proposed landing sites are chosen near regions that show radar anomalies suggestive of underground cavities. If any of them hide water, future crews would be positioned to test drilling strategies and map their interiors. A proven ice-bearing tube could become the anchor for the first permanent base, a combination shelter, laboratory, and resource plan under a common roof. If none contain ice, they still offer sites for safe, shielded construction, reducing the burden of long-term survival on the exposed regolith. In many ways, the discovery of accessible caves on the moon is as significant as confirming ice in a crater. They are part of the same puzzle: how volatiles survive in environments we once thought impossible, and how geology, not just sunlight, controls their fate. Yet even as these underground structures promise stability, there are hints from other investigations that something less tangible might also shape where water can persist. Subsurface insulation may not be the whole story. Those hints arise from another kind of measurement, not of water, but of magnetism. And just like the story of lunar hydration, the signals first appeared faint and confusing, only to deepen into a mystery that still resists easy answers. The moon's strange magnetic scars. For most of the space age, the moon was thought to be magnetically quiet. Any internal field it once had was believed to have faded billions of years ago, leaving behind only faint traces preserved in ancient rocks. Apollo astronauts did bring home fragments that carried remnant magnetism, but these were interpreted as records of a primordial dynamo that no longer operated. Without a molten, convecting core to generate currents, scientists assumed the moon had no present sources for strong magnetism. The picture felt consistent: a geologically frozen body, chemically arid and magnetically inert. But as spacecraft carried more precise magnetometers, the consistency began to unravel. Certain orbits revealed unexplained distortions. Some probes crossed regions where particle instruments recorded plasma disturbances over specific craters. For years, each anomaly was dismissed as minor or localized interference. Then, with the return of high-resolution data from orbit and new analyses of samples from missions like Chang'e 5 and Chang'e 6, a much stranger picture came into focus. Instead of being uniformly silent, the moon's crust was revealed to contain scattered hotspots where magnetic intensity spiked unexpectedly. These were not traces of a global field, but concentrated zones of localized magnetization, sometimes strong enough for local crustal fields to deflect streams of solar wind particles and create small-scale protective effects. These magnetic scars appear across various regions of the lunar surface, but are especially concentrated in areas of geological and resource interest, including the polar environments believed to harbor ice deposits in permanent shadow. The overlap was more than coincidental in appearance. For many researchers, it raised a key question. Could these crustal anomalies be quietly shaping how volatiles survive on the moon's surface? The return samples have underscored the reality of these magnetic concentrations. Laboratory measurements on lunar soils from Chang'e 6 found high abundances of ferromagnetic minerals, metallic iron and Fe, Ni alloys, that can carry strong remnant magnetization. These analyses reported saturation magnetization values higher than Apollo and Luna samples, confirming that significant populations of magnetic grains still exist in the regolith. The fact that fresh material from the South Pole, Aitken Basin, shows such properties, even in an environment where the modern dynamo field has long since collapsed, demonstrates just how substantial the magnetic memory of the crust remains. In some places, these signals are strong enough to disrupt orbital measurements, forcing a reassessment of decades of data once thought straightforward. Such magnetic anomalies matter because they alter the interaction between the solar wind and the lunar surface. The solar wind, composed of charged particles, typically bombards the regolith directly, implanting hydrogen, sputtering exposed volatiles into space, and slowly eroding surface stability. But where localized magnetism diverts those ions, the environment changes. Even weak patches of shielding can reduce the flux of bombardment, lessening loss rates and subtly affecting how volatiles migrate or remain in place. On long timescales, these protective effects could mean the difference between an ice deposit persisting for eons or diminishing away. In this view, lunar water is not governed by cold traps and shadows alone. Instead, invisible magnetic overlays may contribute a second layer of defense shaping, where usable pockets of moisture survive. The South Pole, Aitken Basin, offers one of the clearest case studies. It is the largest and deepest impact basin on the Moon, stretching more than 2,500 kilometers across. Along its northern rim, orbital magnetometer data reveal pronounced crustal anomalies, while its central interior shows much weaker magnetization. The difference is thought to arise from the distribution of impact ejecta and the composition of material reworked during immense collisions. The Chang'e 6 soils came from within this basin, and their magnetic measurements provide ground truth to support orbital charts. Yet the paradox remains. The soils carry a high remanence capacity, but their landing region today shows relatively weak field strength. This suggests that repeated reheating by later events may have demagnetized areas even though the constituent minerals remain capable of carrying strong magnetism. The origins of the anomalies are still debated. One explanation ties them to an ancient lunar dynamo, a convecting, molten core that may have persisted much longer than once assumed. Some Apollo samples record strong magnetization dating back 4 billion years, while others suggest younger episodes around 2 billion years ago. Another hypothesis adds exogenous contributions from iron-rich meteorites. Impact-generated melts mixed with fragments of meteoritic metals could have carried and preserved magnetism upon cooling. A third possibility, modeled in a 2025 study from MIT, proposes that a combination of a weak ancient magnetic field and the plasma cloud from a huge asteroid impact could have temporarily amplified magnetism on the Moon's far side. In their simulations, the flow of ionized material concentrated field lines in localized regions, strong enough that rocks cooling during that interval would lock in unusually high remnant magnetization. Each scenario is testable, but none yet definitive. The anomalies may reflect overlapping influences of internal and external processes operating across very different eras. This uncertainty makes it tricky to pin down the precise link to volatiles. While it is tempting to claim magnetic anomalies directly preserve ice, the connection is more nuanced. Local shielding can lower sputtering rates, but it cannot stop thermal escape in regions subjected to direct sunlight. Conversely, cold traps without shielding can still preserve ice purely through extreme low temperatures. The most realistic view is that magnetism is a partial factor. In some places, where shadow and magnetism coincide, volatile survival may be enhanced relative to equivalent craters lacking residual fields. This could help explain aspects of the irregular distribution seen in orbital and in situ measurements. Still, researchers emphasize the point remains an open area of investigation rather than a settled cause and effect. What emerges clearly, though, is that the Moon's environment cannot be treated as uniform. Every anomaly changes plasma flows, particle implantation, and perhaps subsurface heat transport. Some sites create conditions friendlier to volatile retention, others do the opposite. That variability complicates exploration planning. If future landers or rovers arrive at unshielded sites, they may struggle with resources sublimating faster than expected. Just a short distance away, deposits under magnetic protection could prove far more accessible and durable. For mission design and long-term settlement, knowing which invisible scars provide these advantages could make the difference between success and costly disappointment. The revision to old models has also forced researchers to correct decades of interpretations. Earlier missions assumed the Moon could be analyzed as magnetically inert, and their instrument calibrations reflected that assumption. Now each pass over a known anomaly requires adjustments, mapping hydrogen signatures, modeling thermal gradients, or predicting dust dynamics without accounting for crustal fields risks, mistaking magnetic influences for other phenomena. The recalibration effort is ongoing, but it underscores how blind spots in assumptions cascade through entire fields of data. Magnetism may even tie into thermal properties of the crust. Variations in conductivity around magnetic patches suggest that aligned minerals could affect how heat flows from deeper rock to the surface. Since volatile stability depends on both surface temperature swings and subsurface thermal gradients, this further complicates predictions. A magnetic site might stabilize volatiles through solar wind deflection, while at the same time destabilizing them by channeling heat differently. Understanding these competing influences will require integrated surveys that look at magnetism, temperature, and volatile signals together rather than as isolated layers. Looking ahead, future lunar missions are beginning to account for these discoveries. Instead of drilling in shadow alone, they will combine shadow maps with magnetic field charts to prioritize promising sites. Instruments capable of measuring surface magnetism while simultaneously probing for hydrogen or ice deposits will test whether protected overlaps are more consistent reservoirs. Sample return efforts will refine how magnetic minerals record these conditions, building a deep-time history of both the lunar interior and its surface environment. For human presence, this knowledge could reduce the need for redundant extraction systems if natural shielding already lowers the rate of volatile loss. The lingering mystery, however, is not just practical but historical. What do the scars say about the Moon's past? Were they frozen snapshots of a gradually dying dynamo, or were they formed in brilliant surges when impacts, plasma, and weak fields interacted at dramatic scales? Answering that will link lunar magnetism to broader planetary evolution, offering clues about how bodies lose and retain magnetic engines across solar system history. What is clear is that the moon carries a legacy much messier than the tidy picture once drawn in textbooks. Its scars are neither random quirks nor trivial artifacts. They shape plasma environments, they influence volatile persistence, and they complicate our maps of where humans can find resources to survive. Whether fragile guardians of ice or relics of a vanished dynamo, they represent an active arena of research and a reminder that even in silence, the moon records forces still capable of shaping its surface conditions today. And yet, invisible scars are not the only proof that the moon's story is unfinished. Other signals now indicate it may be more restless than its still landscapes suggest, with unexpected activity continuing to reshape the places we thought would never change. When the moon refuses to sit still, the picture of a geologically frozen moon has lost much of its certainty. For decades it was assumed that nothing beneath the surface had moved in billions of years. Volcanic fires were long gone, tectonic stresses had relaxed, and the quakes that Apollo seismometers once registered were thought to be nothing more than minor thermal contractions. Yet recent geomorphic and remote sensing studies have overturned this view. In 2025, researchers analyzing lunar reconnaissance orbiter data identified 266 small ridges on the far side of the moon. Their crisp edges and lack of impact weathering mark them as geologically young, formed within the last 200 million years. At roughly the same time, laboratory studies of samples brought back by the Chang'e 5 mission revealed volcanic glass beads dated to just tilde 123 plus or minus 15 million years ago. Together, these findings show that the moon has experienced both tectonic deformation and volcanic activity far more recently than previously believed. Instead of a silent husk, it has been active well into the last few 100 million years. The evidence also reframes Apollo's earlier seismic results. Moonquakes were once attributed entirely to surface cooling, a passive process requiring no ongoing internal heat. But the distribution of the recently discovered ridges, folds and scarps that match the lineaments of faults, suggests crustal motion is still capable of reshaping the terrain. The ridges form when the moon contracts as it continues to cool over time, forcing rock upward along thrust faults. Gravitational stresses from Earth's pull can amplify that effect, producing surface shifts even now. If faults are young, then motion along them today remains possible, which explains why seismometers consistently detected bursts of activity that never quite fit the tidy narrative of a moon gone still. For settlements planned near the poles, this unsettles old assumptions. A ridge that formed within the last 200 million years is practically modern in planetary terms. If such features are still developing, polar ice reserves may not be sealed in ancient stability. Instead, they sit in a landscape vulnerable to movement. Quakes can expose buried ice, making fresh samples accessible, but they can also destroy protective traps, releasing reserves into space. That dual reality is stark. Quakes can expose ice, good for sampling, or destroy traps, bad for long-term extraction. Chang'e samples strengthen the case further. The volcanic glass beads found in 2020 and published on in subsequent years are distinct from impact-generated melts. Their sulfur isotopes, textures, and rare earth enrichments point to magma sources heated by radioactive elements within the mantle. The fact that eruptions persisted until only about 120 million years ago means the lunar interior retained localized pockets of heat long after global volcanism ceased. This has implications for polar volatiles. If such heating continued in regions beneath the crust, it could have created conduits for gases to migrate upward, aiding in volatile transport to colder zones. That idea dovetails with seismic evidence. Tectonic adjustments may be redistributing hydrogen and water even now, feeding polar traps more recently than the standard models assume. The connection between activity and water supply is not just theoretical. If fractures and scarps continue to form under stress, they provide pathways for material exchange. Solar wind hydrogen implanted in surface grains might migrate through these cracks, settling into colder interiors where shadows protect it. Subsurface volatiles disturbed by quakes may redeposit elsewhere, patching one reserve while draining another. Far from static freezers, polar trenches could be dynamic systems fueled by ongoing geological adjustments. This pushes researchers to consider that the Moon's water cycle may still be evolving, shaped by the planet's contraction and magnetic scars as well as sunlight. For exploration, unpredictability is as much a challenge as it is an opportunity. Artemis planners depend on reliable storage of polar ice to justify infrastructure for bases and fuel depots. But if ridges and the stresses that form them continue to reshape the ground, resource maps will require continual updating. The need for permanent seismic networks has moved much higher on the agenda. Scientists emphasize that understanding ongoing activity demands more than temporary lander stations. Distributed and long-term sensors are needed if we are to distinguish between shallow quakes tied to daily thermal cycles and deeper tectonic releases tied to internal cooling. At present, such a global network does not exist, but it is increasingly discussed as critical for exploration safety. Moonquakes also complicate engineering. Unlike Earth, the Moon's atmosphere cannot absorb vibrations or dampen energy. Seismic waves propagate more cleanly, traveling long distances with little loss. A relatively small release of energy can translate into extensive shaking, dislodging dust and destabilizing slopes. Habitats built near crater rims would be particularly vulnerable. Engineers now factor seismic resilience into designs for lunar bases, envisioning anchored foundations and structures able to withstand dust avalanches triggered by ground movement. There are wider implications for lunar science as well. If geologically young structures exist, earlier maps that assumed static topography need reconsideration. Dating of impact craters, the standard method to determine surface ages, depends on assumptions about background deformation rates. Younger scarps mean parts of the surface have been refreshed far more recently than time counters suggest. This adjustment reshapes not just our understanding of the Moon, but also comparative models for Mercury and Mars, which show similar tectonic contraction features. These developments converge on one important conclusion: assumptions of permanence cannot be counted on. Just as patchy ice distributions defied neat expectations, seismic and volcanic findings show that even the landscape itself continues to evolve. For water, this may be a mixed story. Renewed fractures keep cycles active, allowing new stores to form. Yet reservoirs can also drain through the same pathways. Future missions must account for both outcomes in order to avoid planning around false certainties. Understanding resource availability therefore demands more than orbital detection. Orbital instruments can record hydrogen signatures, but they cannot reveal whether quakes have recently disturbed the deposits or altered their distribution. Surface and subsurface monitoring will be vital to address that gap. Without it, explorers risk discovering that a promising patch has already been destabilized. The persistence of young ridges and recent volcanism makes the Moon far less predictable than old models implied. And this unpredictability connects directly to surprises waiting in surface measurements. The tendency for features to shift, redistribute, or vanish complicates the interpretation of resource maps made from orbit. What appears plentiful from a distance may not be accessible after all. That unresolved tension between expectation and ground truth sets the stage for the next challenge, where predictions of abundant resources meet the stark reality of direct measurement. The puzzling absence problem. When India's Chandrayaan-3 rover began making direct surface measurements, expectations were unusually high. For years, orbital maps had suggested hydrogen concentrations scattered across the South Polar region, especially near permanently shadowed craters thought likely to conceal water ice. Instruments aboard multiple spacecraft, from neutron detectors to infrared spectrometers, had all reported signals consistent with hydrogen and hydroxyl. By the time Chandrayaan-3 rover rolled onto the terrain in 2023, the idea of confirming water right at the surface felt almost routine. That is why what it measured was so striking. Using its laser-based spectrometer and alpha particle X-ray spectrometer, Pragyan found no clear hydrogen signature in those surface patches. For a mission aimed at a region long advertised as hydrogen-rich, the immediate absence was unexpected. On one level, it seemed straightforward to dismiss this as a correction of faulty maps. After all, orbital measurements are indirect. Neutron flux and reflected spectra are open to interpretation, and analysts must account for noise, varying angles, and interference from minerals. But that quick dismissal does not hold. Signals mapped across the polar terrain had been consistent for decades, confirmed by multiple orbiters and instruments working in different wavelengths. The absence seen by Chandrayaan-3 could not be explained away as a single glitch. Something more fundamental was happening, and it exposed what researchers are now calling the Moon's puzzling absence problem. The explanation may lie in the difference between orbital sensing and rover sampling. Neutron detectors on orbiters penetrate below the immediate surface, reaching tens of centimeters into the regolith. What they measure is essentially an average signal, influenced by subsurface content as well as what sits on top. By contrast, Pragyan's instruments analyzed material directly exposed at the surface, the top few millimeters of soil. If hydrogen compounds sit even a few centimeters deeper, buried beneath that upper veneer, the rover would not detect them. The null result then no longer contradicts the orbital maps, it defines their limits. Helpfully, Vikram, Chandrayaan-3 lander, carried an instrument specifically designed to read subsurface conditions. Its probe, Chang'e, measured how heat moved through the regolith. The results were striking. At the surface, daytime temperatures climbed close to 60 degrees C, but just 8 centimeters down, the probe recorded values near -10 degrees C. That rapid gradient highlights just how effectively lunar soil insulates. Within a hand's depth, the environment shifts from hot enough to drive off volatiles to cold enough to preserve them. In other words, it is entirely plausible that orbital instruments sense hydrogen buried out of reach, only centimeters below Pragyan's analytical tools, a difference large enough to mean the rover missed ice hiding directly beneath its path. This interpretation reframes the absence not as a contradiction but as a clue. It implies the Moon's regolith functions as a thermal and physical barrier, protecting water ice from erasure while leaving the exposed surface barren. Over billions of years of bombardment by micrometeorites, the uppermost soil has been continually stirred, resurfaced, and desiccated. This gardening reaches only shallow levels, just deep enough to strip the upper grains. What lies beneath stays sealed away, undisturbed and insulated. Pragyan's lack of hydrogen detection may simply mark the depth limit of its instruments, not the limit of actual resources. Recognizing this helps reconcile decades of odd signals. When earlier landers or seismically shallow drills failed to find water, scientists assumed contamination or error. But those missions were never designed to sample beyond the top of the soil blanket. Even Apollo's drills, impressive at the time, probed only a handful of meters in equatorial zones far from the poles. If polar hydrogen is consistently buried beneath a dry crust, then surface sampling, then and now, would all deliver the same misleading silence. Chandrayaan-3 results, instead of falsifying the presence of water, may underline the need to approach it differently. This mismatch introduces practical difficulties. Missing hydrogen in surface assays means mission planners cannot treat orbital maps as exact dig-here instructions. For Artemis crews, or for private companies hoping to mine lunar water, the lesson is pointed. Access may require drilling deeper than initially assumed. Lightweight scoops or shallow scrapers will not suffice if usable reservoirs are consistently buried beneath insulating dust. Heavy drilling rigs and powered augers designed for meters, not centimeters, may be necessary. That in turn adds weight, complexity, and cost to missions. Payload budgets once reserved for cruise systems or scientific instruments may need to be diverted to excavation equipment. On the other hand, if deeper caches prove substantial, the investment pays off with lasting supplies, far more valuable than a thin frost scraped from the topsoil. The practical questions expand beyond equipment. In situ extraction strategies rely on understanding the temperature profile of the regolith. As Vikram's probe showed, insulation is steep even within a shallow layer. Hydrogen resting just beneath a few centimeters of dust sits at stable, sub-zero temperatures, effectively bottled away from the violent swings above. That stability means the resource can persist for geological timescales, unaffected by the photodissociation and sputtering that strips surface grains. This resilience strengthens the argument that orbital measurements are detecting something real, just hidden deeper than Pragyan was able to reach. In this sense, Chandrayaan-3 reminds us of the limits of remote sensing. Orbital data remains invaluable for global context, but without ground truth, interpretations invite missteps. The rover's silence does not reflect a flaw in orbital maps. It reflects scale mismatches between averaged signals and shallow probes. Moving forward, scientific models must fold these layers together, acknowledging that volatiles exist in stratified distributions. Surface soils may be dry, overlying reservoirs that satellites correctly detect, but rovers fail to touch. The consequences for planning are significant. Artemis and follow-on programs intend to scout sites near the lunar South Polar region. If surface materials are routinely barren, selecting a landing site based only on orbital values risks costly disappointment. Detailed maps that integrate both orbital averages and simulation of regolith structure will be key. Even then, validation must come from drilling. No one can simply assume that a patch of polar dust highlighted in global charts is directly accessible. Only deeper sampling will confirm whether reserves sit waiting just out of reach. The absence problem also presses a broader scientific point. For decades, discoveries of lunar water moved in a single direction, from denial to acceptance, as evidence accumulated. But Pragyan's data slows that progression, forcing researchers to face lingering uncertainties. The moon's volatiles are not neatly arranged or predictably exposed. Instead, they are layered, buried, scattered, and sometimes hidden right beneath the rover's wheels. Local geology, faults, regolith churn, the shadow of crater walls, complicates predictions far beyond the simple rule of shadow means ice. Confronting that complexity is vital if resource science is to advance beyond broad conjecture. At the same time, the hidden reservoirs may enrich science as much as they aid exploration. Buried ice preserved under insulating regolith could record ancient solar wind implantation, cometary delivery, or volcanic outgassing. Digging deep enough to retrieve intact samples would therefore give not only usable water, but also a geological history lesson. Each core of ice and dust would act like a capsule from different epochs of the moon's volatile story. Conservation under insulation could mean more than survival resources. It could open direct paths into studying the ancient sun, Earth, and solar system. What Chandrayaan-3 established is that the surface alone will not solve the puzzle. Hydrogen is present according to satellites, absent at the exposed regolith, but likely preserved just beneath. To move forward, missions must be equipped to dig where current rovers merely scan. Only then will the answer shift from absence to verification. And as exploration gears up for deeper access, the unavoidable question follows. If water hides beneath a thermal blanket only centimeters thick, how do we find it? That's where smarter drilling comes in. The difficulty, however, is that even if we probe further, another obstacle immediately surfaces: the sheer variability in how much water the moon actually holds. Numbers that don't add up. When scientists first began estimating how much water the moon might hold, the numbers seemed manageable. Early projections from missions like Lunar Prospector suggested totals in the tens of millions of metric tons, while some models leaned toward hundreds of millions. Though the range was wide, it felt narrow enough that exploration plans could treat the figures as a reasonable baseline. By 2025, that sense of confidence had unraveled. Updated orbital maps, thermal models, and the first ground-based data from landers and rovers produced estimates that stretched from a few tens of millions all the way to several 100 million metric tons. That spread no longer looks like small differences in interpretation. It represents radically different futures. At the low end, water is just enough to support cautious, temporary outposts. At the high end, it becomes a vast reservoir that could fuel long-term settlements and even enable missions deeper into the solar system. Instead of converging on clarity, the numbers drifted apart. The reason for this divergence is tied to how measurements are made. No single instrument can look into the lunar soil and directly weigh its ice content. Instead, spacecraft work through proxies. Neutron spectrometers detect variations in hydrogen by measuring particle flux. Infrared spectrometers map absorption features that resemble water or hydroxyl molecules. Radar instruments probe for reflections, hinting at buried layers with unusual dielectric properties. In addition, impact missions scatter material into sunlight to quickly measure whether volatiles are present in the ejecta. Each of these techniques captures a piece of the puzzle, but none of them tell the whole story. Hydrogen detection doesn't prove ice, just as an infrared signature can't show whether molecules are chemically bound or physically frozen. And impact plumes measure only a single location at one moment in time. Put together, the methods produce information that is valuable but incomplete, leaving scientists with estimates that vary depending on which indicators and assumptions they emphasize. Most researchers assumed that as more data accumulated, those estimates would begin to narrow. Yet instead of stabilizing, each new round of measurements widened the uncertainty. When Chandrayaan-3 found no hydrogen in its surface tests where orbital maps predicted it, confidence in earlier surveys wavered. Scientists suggested that perhaps the water was buried deeper than the rover's instruments could test, or the orbital readings had averaged in hydrogen from adjacent areas. Each suggestion fed new models, and those models diverged even further in projecting total reserves. NASA, ESA, CNSA, and other programs each applied their own interpretations, and the resulting charts emphasized different parts of the spectrum, from conservative estimates at the low tens of millions of tons to optimistic scenarios climbing above 200 or 300 million. Three main factors drive the spread. First, detection methods measure different things. Neutron counts, spectral features, and radar reflections do not all observe the same phenomenon, so their conclusions don't align easily. Second, depth is an unresolved variable. Some models assume volatiles are shallow and accessible. Others put them meters down, changing total calculations. And third, the moon's water is not uniform. It clusters in patches, sometimes concentrated, sometimes absent just a short distance away. Averaging scattered data over wide areas exaggerates these inconsistencies, sometimes inflating totals, sometimes undercutting them. Together, these three elements explain why credible estimates remain so wide apart. The consequences for planning are direct. Engineering a short-term landing mission with modest life support goals is very different from designing infrastructure around large-scale extraction. If water is closer to the lower estimates, crew survival will still depend on costly shipments from Earth and careful rationing of reserves in situ. If higher estimates are closer to reality, then the moon becomes a staging point for producing rocket fuel, supporting exploration of Mars or asteroid mining ventures beyond. The uncertainty between those two scenarios translates into major differences in what builders choose to send, how missions are staged, and when permanent bases become practical. Beyond engineering, the lack of agreement shapes mission priorities. Space agencies are leaning heavily toward landers with drills, seeing no alternative to direct sampling at depth. Rovers equipped with 1-meter drills, such as NASA's Viper, are scheduled to explore regions of interest, but deeper drills capable of 10 meters or more will eventually be necessary to resolve hidden pockets. Until then, models will remain contested. Each new mission risks adding more complexity, because surface results and orbital averages rarely match exactly. Only by tying surface chemistry readings to stratified cores taken from subsurface layers will scientists narrow the totals enough to guide long-term planning. The uncertainty is not just about absolute amounts. It's about accessibility. Ice buried 50 centimeters down is far easier to reach than reserves sealed 10 meters beneath fractured rock. A pocket of hydrated grains scattered through soil yields much less usable water per kilogram than a concentrated layer of true ice. Current models rarely agree on whether hydrogen signals imply concentrated deposits or thin dispersals. This ambiguity means the same orbital reading could represent either a usable reserve or a frustratingly lean source. Until drills prove otherwise, any total remains provisional, with accessibility perhaps proving more important than volume alone. For international programs, the disparity adds complexity. Each agency points to different analyses, shaping where they want to send their landers and how they prioritize exploration zones. Competition builds not just around who will reach the lunar poles first, but around who will secure answers to the uncertainty that all others must then adapt to. A verified discovery of rich deposits would instantly reset strategies for everyone else, compelling partnership or rivalry, depending on the scale of what is found. The gap of tens versus hundreds of millions of tons is large enough to set entire exploration roadmaps in different directions. The irony is clear. Not long ago, the argument was whether any water existed on the moon at all. Those doubts have long since ended. What faces scientists now is a more subtle problem: abundance, distribution, and reliability. Too little means fragile logistics dependent on imports from Earth. Too much, if the higher limits are correct, means a transformative leap in capabilities for settlement and propulsion. Every close inspection so far has deepened the uncertainty instead of resolving it, reminding researchers that remote sensing cannot bridge the final gap. That is why attention remains fixed on drilling missions through the rest of the 2020s. To capture cores at different depths and across different terrains will finally offer the measurements strong enough to resolve the scale. Once that data is in hand, agencies can commit to clear architectures, whether to design around scarcity or abundance. The moon's water totals will define its role in humanity's next century of exploration. What is at stake is not only the science of how lunar volatiles survive, but the practical ability to use them. The difference between narrow reserves and vast stores is the difference between temporary presence and permanent infrastructure. And the only way to move from competing estimates towards certainty is to go down into the soil and find out. For now, the totals remain somewhere in that range of tens to hundreds of millions, unproven and elusive. The moment they resolve, decisions about everything else, bases, fuel depots, even Mars missions, will follow quickly. But what matters just as much as how much water exists is what that water can actually do once it is put to use. It is not only about numbers on a chart, it is about what those numbers make possible. And that, more than the disagreement over totals, is what gives lunar water its real promise. The promise of humanity's ice wells. When planners look to future missions, the discussion about lunar water quickly shifts from survival to strategy. Drinking and growing plants matter, but splitting water into hydrogen and oxygen matters even more. Those two elements form the basis of rocket propellant, the cornerstone of in situ resource utilization, ISRU, outlined throughout NASA's Moon to Mars architecture papers. If you can refuel a ship on the Moon instead of hauling fuel up from Earth's deep gravity well, the economics of exploration change overnight. Lunar water becomes infrastructure, not a supply item, but the enabling layer for every mission that follows. If propellant can be made on the Moon, then crewed missions to Mars gain a direct refueling stop before setting out. That is why the Artemis program treats water as more than a survival resource. It treats it as the foundation for expansion. This is why the language of sustainability keeps surfacing in Artemis planning documents. Apollo was designed for short visits, flags, rock samples, and exit. Artemis is keyed to permanence. Crews aren't going to the surface for days, but for stretches long enough to demand reusable systems and local infrastructure. In practice, that means fewer cargo rockets constantly lifting supplies from Earth and more hardware that regenerates or replenishes what astronauts need. The difference is stark. A ship that arrives with all of its fuel on board has a fixed ceiling for what it can do. A ship that can refuel from lunar wells becomes part of a system, launching from depots, hopping further than before, and expanding the reach of exploration in ways Apollo could never attempt. The designs for base camps being written in 2025 reflect this philosophy. Modularity is the guiding principle. Instead of a single massive mining facility, multiple small extraction units are envisioned. Each can function independently, drilling into the regolith or scraping ice, electrolyzing water into oxygen and hydrogen, and pumping reserve tanks without requiring a central hub. Power is drawn from solar arrays set along crater ridges, or from compact nuclear sources designed to sustain operations through the darkness of the 2-week lunar night. By distributing extraction units, mission planners hedge against failure. If one stops working or a particular patch of regolith turns out dry, others can continue operating. The approach looks less like one city-wide grid and more like a network of scattered wells, each one built, tested, and maintained as the system grows. The near-term embodiment of this approach is Artemis III. While most attention outside NASA frames it as the first crewed landing in half a century, within planning circles it is understood as something more basic, the first opportunity to pair human activity with tested resource extraction. The tools sent alongside the astronauts will not be industrial rigs. They will be compact pilot systems, equipped with heavy instrumentation. Their goal is to show whether lunar ice and hydrated soils can actually be drilled, processed, and converted in a closed circuit on site. Success provides the data needed to scale up in Artemis IV, and failure still provides vital feedback. Either way, Artemis III is structured as a hinge moment between theory and practice. Private companies extend the blueprint. SpaceX and Blue Origin, already building landers, also promote designs for surface refineries that move on robotic platforms. Instead of anchoring one massive machine at one site, they envision mobile processors that adapt to the patchwork distribution of ice, skimming what's available and relocating when reserves decline. Other concepts propose underground chambers where extracted water is stored safely away from sunlight, effectively a vault for future crews to draw from. The private sector angle matters because it shifts resource planning from a purely national program to a commercial service model. Lunar surface operations become a market, each company staking its place in building the wells of a future lunar economy. The payoff is obvious. An astronaut crew landing near the South Pole no longer depends wholly on supplies imported from Earth. Pumping water through electrolysis units feeds directly into breathable oxygen, drinkable reserves, and high-energy propellant. The same tanks that collect hydrogen and oxygen can refuel ascent stages returning to lunar orbit or outbound vehicles aimed at Mars. Artemis architects call this closing the loop. It ties every part of the system together: habitats, rovers, power systems, launch pads, because all of them depend in some way on water. Add to that another bonus: Reserves also serve as excellent radiation shielding. Tanks placed along the walls of living modules help reduce exposure to cosmic rays and solar flares, creating safer long-duration habitats. One resource satisfies multiple needs. This doesn't erase the risks. Orbital maps and surface surveys still disagree about abundance. Artemis teams cannot guarantee that every targeted crater will yield usable reserves. That uncertainty is built into the design. Units are modular so they can be moved. Power stations are decentralized so they can extend operations in stages. Even supply depots are planned as multiple distributed storage tanks rather than single centralized farms. With that design philosophy, resilience takes priority over efficiency. The assumption is not abundance but scarcity, managed by flexibility and replication. Another dimension is international. Artemis by itself is not carried by a single nation. The European Space Agency supplies Orion's service module. The Canadian Space Agency develops robotic systems. Japan contributes in logistics and cargo delivery. Each partner adds hardware designed to integrate with NASA's core infrastructure. Shared systems ease cost, but more importantly, open redundancy. If modules from one agency falter, others can help sustain the loop. For lunar water specifically, international contributions mean more opportunities for testing, more extraction units deployed, more chances to validate the presence of usable reserves. Water unites not just machinery, but global partners in a shared network. The obstacle pressing against all of this is money. Budgets proposed for 2026 outline steep reductions to NASA's funding, slicing billions from Artemis plans. At the same time, they lean into commercial firms to pick up the gap, reframing extraction and infrastructure as services that private companies own and operate. If that pivot holds, the moon's water becomes entangled in a hybrid economy, part government exploration, part commercial supply chain. Advocates argue that private pressure will accelerate innovation by letting multiple groups compete. Critics warn it could fracture into incompatible systems and leave sustainability vulnerable to market forces rather than stable investment. What is not debated is the central role of water itself. With or without federal budget certainty, no version of permanent lunar presence bypasses local ice. What stands out in 2025 is how concrete the planning has become. Speculation about whether water exists has given way to engineering diagrams assuming its presence. Tanks for shielding, electrolysis chambers for propellant, pipelines linking modular units. Artemis treats water not as a variable but as the load-bearing structure on which every mission depends. The only unknown is scale. How much extraction systems can draw at once, and whether the network can keep pace with human and robotic demand. There will be surprises. Units may land on patches that turn up drier than orbital data suggested. Hardware may struggle against lunar dust or extreme cryogenic temperatures. Yet the philosophy of dispersion, redundancy, and mobility means those failures will not end the effort. They simply redirect it. For the first time since astronauts last stood on the surface, hardware is arriving not just to survive but to build permanence, turning the moon itself into part of humanity's operating environment. That permanence is what gives lunar ice its broader significance. It is more than a scientific subject. It is the keystone of a logistical system. And wherever systems like this emerge, questions of control inevitably follow. The crowded race for lunar resources. At the lunar South Pole, attention is shifting from exploration to access. Nearly every major space program, along with several private companies, is turning its focus to the same narrow terrain. The attraction is simple. This is where water is most likely to exist in usable quantities, locked in shadowed craters and layered beneath the regolith. And because water doubles as fuel and life support, these sites carry strategic weight. Multiple national programs, NASA's Artemis partners and China's Chang'e missions, are converging on the pole, raising the stakes of whatever future discoveries prove the presence of confirmed ice. For the United States, Artemis is intended to re-establish human presence on the surface and then make it permanent. The program's designs, from modular base camps to local energy grids, lean heavily on the assumption that ice will be accessible. NASA's Viper rover, scheduled for launch later this decade, is tasked with drilling directly into polar regolith to map those resources at the ground level. Alongside it, American contractors through the Commercial Lunar Payload Services Initiative are preparing landers of their own, scouting ridge lines and crater rims in the same region. The South Pole, before a single base is complete, is already at risk of becoming overbooked with missions heading to the same square kilometers of terrain. China's Chang'e program is moving deliberately but steadily toward the same goal. Chang'e 5 returned samples from Oceanus Procellarum in 2020, and Chang'e 6 brought back new material from the South Pole, Aitken Basin in 2024. These were not symbolic milestones, they built capacity. Each mission extended technical experience, from automated sampling to far-side operations, with the clear intent to support a crewed landing. Official projections target a human presence before 2030. This timetable intersects uncomfortably with Artemis plans. Neither Washington nor Beijing describes the situation as a race, but both are operating on converging trajectories, with their eyes on the same permanently shadowed craters. The issue is not abstract competition. It is practical infrastructure. Ice is finite. Once mapped and confirmed at any single site, it can be claimed in practice, not through legal title, but through working systems that gain de facto control of access. On Earth, the first ports define trade routes for generations. On the Moon, the first functioning ice wells could shape decades of resource distribution, not only for local use, but for missions extending outward to Mars and deep space. Whoever builds credible infrastructure first gains essential logistical leverage. To frame this growing competition, NASA has put forward the Artemis Accords, a set of voluntary principles for civil space exploration. More than 20 nations have signed, agreeing on transparency, interoperability, and mutual assistance. The idea is to prevent disputes by setting norms ahead of time, yet not all have joined. China, Russia, and some other nations remain outside. That leaves the prospect of parallel frameworks governing behavior on the Moon, with no unifying treaty to enforce standards. In practice, the first program to demonstrate sustained extraction would likely set precedent by default, shaping expectations long before new agreements could be drafted. This does not mean legal ownership, but it does suggest strategic and commercial advantages that persist well into the future. Here is where domestic realities intrude. For the United States, sustaining Artemis depends on consistent funding. The fiscal year 2026 budget proposals include substantial reductions for NASA, raising the risk that projects beyond Artemis III might be delayed or canceled. Components such as the Lunar Gateway, a station to serve as a staging post in lunar orbit, are already under review. Advocates argue private industry can take on these roles, accelerating innovation under commercial competition. But private actors also carry conflicting motivations. Profit, risk tolerance, and investor schedules can misalign with long-term global partnership goals. Gaps left by government investment may be filled, but filled unevenly. China's approach reflects the opposite structure. Its program is insulated from budget votes and electoral changes. The progression from Chang'e 3 to Chang'e 6 illustrates a consistent trajectory: incremental testing, sample returns, and orbiter-lander coordination. By controlling the process centrally, Beijing ensures steady development, even if less flexible or open to private innovation. That steadiness raises a different question altogether. What if China achieves working polar extraction before the United States and its partners? The change in perception would be symbolic, but it would also be practical. International logistics, from navigation beacons to cislunar transport routes, might develop under Chinese precedents rather than American. The South Pole's value is not only its ice. The region also offers ridge lines that remain sunlit for much of the lunar year. These peaks of near-eternal light provide reliable solar energy, critical for operations otherwise forced to survive the long lunar night. The combination of trapped volatiles below and sunlight above makes the polar terrain uniquely suited to settlement. That double incentive is why so many competing missions are focused on the same handful of craters and cliffs. As more programs converge, risks grow. Unlike orbital space, where satellites can spread across altitudes and inclinations, surface sites on the South Pole are limited by geography. Dozens of missions crowding onto overlapping targets creates a high likelihood of interference. Even minor errors could cascade. A lander leaking propellant on nearby regolith, a rover stirring up dust that contaminates another site's instruments, or competing drills targeting the same resource. The legal frameworks to resolve such problems remain weak, and the thin margin for error magnifies the potential for disputes. For Europe, Canada, and Japan, partners contributing directly to Artemis, these challenges link their own space ambitions tightly to U.S. decisions. Orion's service module, Canada's robotic construction systems, and Japan's logistics all rely on Artemis infrastructure remaining intact. If budget cuts or policy shifts weaken the program, their contributions risk being stranded without operational support. This dependency underscores why some allied partners view their involvement as both opportunity and vulnerability. At the same time, private industry is aligning with both sides of the competition. American companies like SpaceX and Blue Origin develop landing systems under NASA contracts, but their designs also envision independent settlement infrastructure. China pursues a centralized model, but has invited international partners for specific technical cooperation. The result is a complex overlap of national programs, commercial ambitions, and scientific exploration, all pressing toward the same terrain. This is an unusual intersection of science and geopolitics. Missions built to answer technical questions: how much ice exists, how deep it lies, how stable it remains, cannot avoid political consequences. Once the first liters of water are pumped from lunar soil, extraction becomes more than an experiment. It becomes precedent. Choices about how that water is distributed or sold will influence the next century of spaceflight. That is why transparency, shared norms, and prompt ground truthing matter. If those steps are skipped, the Moon's South Pole risks becoming a theater of logistics and politics rather than an arena of science. For now, the region is unchanged. The shadows remain dark, the ice deposits unconfirmed, and the contested terrain untouched by sustained extraction. Yet the countdowns have already begun. Each pending mission looks toward the late 2020s as the decisive moment, when the first real wells might open. At that point, competition turns into operating systems and maps turn into infrastructure. And as programs brace for that threshold, the spotlight also shifts back to the question that started it all. After decades of missions, why is the picture of lunar water still so unsettled? The bigger mystery about lunar water. For half a century, the search for lunar water has seemed like a puzzle with too many scattered pieces. Every new mission has added data, yet the overall picture remains unsettled. From orbit, the story seems straightforward. Hydrogen signatures show up across the poles, hydration features appear in sunlit regolith, and radar hints at buried ice in shadowed craters. The signals come from multiple instruments: infrared, neutron detectors, and radar systems, all pointing to water in some form. Dismissing that as coincidence no longer holds. And yet, when landers or shallow drills test the same regions, the results often come back with little to nothing. Chandrayaan-3 confirmed this mismatch in 2023, and missions like NASA's upcoming Viper rover are explicitly designed to investigate it. Summed up, orbiters keep flagging hydrogen widely, while instruments on the ground often return near zero. That contradiction sits at the heart of the bigger mystery about lunar water. If orbital data had been mistaken, later missions should have corrected the error. If surface instruments told the whole story, we would no longer be arguing. Instead, the disagreement persists. The orbiters keep reporting hydration in too many regions and under conditions too scattered to ignore. The rovers and landers, on the other hand, test specific sites and often run into barren patches. This uneasy balance, abundance from above, scarcity from below, forces scientists to reconsider not just where lunar water is, but what form it takes, how it moves, and whether our definitions fit the evidence. Decades ago, the models were simple. The moon was treated as a passive body that could preserve water if it landed in a cold, shaded pocket, or lose it quickly in sunlight. Following that logic, one could map water by overlaying thermal profiles with shadow maps. Yet the reality strays from that neat framework. Hydrogen shows up in equatorial regions that receive constant sunlight. Polar craters that should act as perfect cold traps sometimes come up empty. Wide orbital sweeps suggest deposits across much of the surface, while carefully positioned ground measurements return almost nothing at all. The moon is either moving its volatiles in ways we don't understand, or the forms of water it hosts are far more diverse than we expected. The mistake may be treating lunar water as if it were a single substance. In practice, it may refer to several distinct phenomena. Hydrogen atoms implanted by the solar wind that drift across the surface before settling into colder soil, hydroxyl groups bound to minerals, or true ice buried beneath regolith at depth. Orbiters could be mapping the mobile, chemical forms spread across dust grains, while landers search for concentrated blocks of ice that are not there to be found. In that case, both sets of instruments are correct, but they are measuring different things. This possibility explains why totals swing so widely. Teams summing orbital reports of hydrogen absorption might project tens or hundreds of millions of tons. Engineers interested in ice mining, however, count only solid deposits that can be extracted and used. The difference between seeing hydration writ large and seeing usable ice writ small can shift estimates by an order of magnitude. Yes, the moon has hydrogen and signs of water. No, usable ice is often missing at drill depth. The real question is, in what form do these molecules exist and how accessible are they? The dynamic behavior of volatiles adds to this uncertainty. If solar wind implantation supplies a constant stream of hydrogen that hops across the surface, the distribution of water is not a frozen map, but a constantly shifting balance. An orbiter might capture one stage in that movement, while ground gear drills into a spot that, at that moment, has nothing concentrated enough to register. This would explain why signals repeat in orbital scans, but localized attempts often appear dry, like measuring a snapshot of traffic without seeing the road network that connects it. Chemistry complicates the picture further. Many orbital techniques cannot distinguish between water molecules H2O and hydroxyl groups OH. Both absorb near-infrared light in similar ways, which means orbital maps by themselves cannot tell whether the signal represents water that could be melted and used or simply chemical bonds present in minerals. A lander or rover probing for extractable ice will not detect hydroxyl, even if orbiters see strong hydration signatures. In that sense, the contradiction is less about error and more about different instruments applying different definitions of what counts as water. This definitional gap helps explain why the science community struggles to agree on totals. If hydrated minerals are included, the moon looks globally coated with water. If only extractable ice is counted, then reserves shrink dramatically. It is not that the moon contradicts itself, but that competing questions, how much hydrogen is there versus how much usable resource exists, demand different answers. From an engineering standpoint, only the ice matters. From a chemical standpoint, every trace is worth measuring. Until those categories are separated clearly, estimates will continue drifting. These contradictions also ripple back into origin theories. If water is found across sunlit equatorial soil, then continuous solar wind implantation might be replenishing it, rather than leaving behind ancient remnants. If ice lodges deep inside lava tubes, it could be primordial, delivered by comets, embedded early, then protected from sunlight for billions of years. If magnetism or tectonic movement influence hydrogen migration, then what we see might be a system that actively redistributes volatiles even now. Each mission supports fragments of these theories, but no single explanation fits them all. The moon starts to look less like one stable body and more like a patchwork test site of interacting processes. For engineers, this is frustrating. Extraction hardware depends on resources being locatable and predictable. Planning a base around a dry patch would be devastating. But for scientists, the contradictions open more interesting doors. If lunar water is active, moving from surface to shadow, binding and unbinding chemically, sheltering in mineral grains, then it is not just a resource. It becomes a laboratory for understanding how planetary surfaces interact with their environments over millions of years. It shows how even airless bodies like the moon remain dynamic, reshaping their surfaces molecule by molecule across time. Chandrayaan-3 data captures this contradiction in miniature. Orbiters marked its landing region as hydrogen-rich, yet its spectrometer results came back barren. The planned Viper rover will drill up to a meter beneath the surface, testing whether subsurface reserves explain the uneven results. If it finds concentrations that orbiters see but shallow landers miss, scientists will finally be able to unify 2 decades of mismatched readings. If it doesn't, the mystery only deepens. All of this creates a lingering tension. Either we have misread the signs of hydrogen from orbit, or the moon behaves in ways our models cannot yet describe. Both options demand caution. The first calls for recalibrating decades of maps and resource estimates. The second implies that every polar deposit survives only conditionally, moving in cycles sensitive to shifts we don't yet track. For exploration planners and scientists alike, that leaves every base design and every fuel extraction plan resting on uncertain ground. And that may itself be the clearest point. We know the moon holds water in some form. We know much of it is not where or what we expected. What we lack is agreement on whether it is frozen, buried, bound, or dynamic. That uncertainty is reason for both frustration and excitement. For crews relying on ice for survival, the lack of clarity threatens logistics. But for science, it is exactly what makes the moon worth studying. It resists simple answers, keeping its processes alive to observation even now. That finally brings us to the payoff. The contradiction is no longer just a scientific quirk. It is the defining theme of exploration strategy. Every decision, landing zones, drilling technology, international agreements, depends on resolving whether the moon is a modestly hydrated desert or a frozen reservoir waiting to be tapped. That uncertainty is why the coming missions are exciting. They will show whether the moon is a working supply depot or a natural museum, holding samples of volatile processes that stretch back billions of years. What is certain is that the mystery has not slowed exploration, it has driven it. Scientists once pictured the moon as a static relic. Now, they see a shifting system whose secrets will shape the future of exploration. And it is this recognition, that water is not just present but unpredictable, that sets the stage for the next realization about our nearest neighbor. We once treated the moon as simple, dry, static, and unchanging, but the record now shows the opposite. Orbital data points to hydrogen across the poles, while surface probes often measure little or none. The question is no longer is there water, but how and where does it exist? The truth is we still don't fully understand how lunar water forms, moves, or survives. Each mission exposes more contradictions than clarity. Would you send the next rover to drill deeper or to map more widely? Tell us below. The next great discovery might be beneath our boots, not beyond the stars.